Welcome everybody to Rochester Security Summit 2024. If you haven't silenced your phones yet, please take a moment to do that. We would like to start by thanking all of the sponsors here at the conference this year. It helps make things a little nicer. Now, getting down to business, I'd like to introduce our two speakers today. Starting with Monica Polak from the University of Rochester in computer science, and TJ Borrelli, Rochester Institute of Technology. There are a few other writers for the paper. I'll try to pronounce their names correctly. Stanislav Radoslavsky and Sumitra Mishra. Good luck, folks.
Thank you.
Thank you for the introduction. We are happy to present our work today. So our talk will be a little bit different than the opening talk because we work at universities. So we will tell you about a little bit different perspectives. So our work focuses on developing new course that we launched, and it was successful for 3 years now at 2 institutions. So it all started at Rochester Institute of Technology, and then when I moved to University of Rochester, I transferred that course there. So we are kind of going to talk about Alice and Bob. You know that story, right? And we are going to talk about some communication issues that they might have in future if we will have a quantum resistant, we will have quantum computers that actually work, really well on all possible algorithms. So this is a teamwork, and we were already introduced, and we just would like to say that it is really big advantage to work with within a team with other people. So it was wonderful to work with TJ, Staszek, and Sumita on this project. So you can see the whole team, and Sumita and Staszek are here today with us. So in the future, we are probably going to use a bit different cryptography, and luckily for us, only public key cryptography will be affected in a bigger way. So Alice and Bob, if you know the story, maybe you noticed something weird about the slide, because Bob is trying to send message to Alice. And if you looked at most of the books, usually it's Alice that tries to send message to Bob. But we like to do things a little bit differently. So as you can see, this is the idea of public key cryptography is that Alice would generate her secret and public key that she would tell to everyone. And then Bob can send a message to Alice. Of course, there might be some bad Eve that might try to interfere with this communication. And we will try to look at future algorithms that will, change. And our main goal was that because some of the algorithms will change, we would like to teach our students about the future authentication and key exchange protocols that we might all have to use at certain point. So the background here is for post-quantum cryptography is that post-quantum cryptography, very often people think that it's post, so that happens after we have quantum computers. However, it actually happens on classical computers. And we don't have to use quantum computations to achieve something that will be secure against quantum computers. Okay, so there is quite some misunderstanding in the name, and actually there is another term that people start to use, which is quantum resistant cryptography, which kind of makes more sense, but people still get used to PQC name. We think it's kind of like surprisingly nice that we can actually have something that is secure against quantum computers, but we can do that on classical computers without actually using quantum computations at all. So on classical computer, but secure against quantum computers. So some basic terminology that we use in our course is quantum computing, which those are actually the computations that can be performed on quantum computers. And we involve some of those in our course because we think that it's really valuable for students to know some of those terms and some idea how quantum computers work so that they will be more motivated and kind of understand like why we have to move to new standards and new encryption algorithms. Quantum key distribution, this is an algorithm, this is a key establishment protocol that can be done on quantum computer actually. And we talk about some of the quantum algorithms in our course to have the idea about quantum computations. Then we talk about post-quantum cryptography, quantum-resistant cryptography, right? Those two terms go together. And this is the study of classical non-quantum systems that actually resistant to quantum computers. And then the other term is quantum supremacy, which is kind of like we are interested at one point in future, eventually quantum computers will outperform classical computers in certain tasks. Okay, so this is like really important for us because if some of the computations can be run really fast efficiency on a large scale, then that might be threat to some of those classical algorithms that we are using those days and that are current standards. So the motivation was, since we teach cryptography for many years, all of us in the team, and we teach those algorithms all the time, which is RSA, and we are big fans of RSA. We also have Diffie-Hellman key exchange, elliptic curves, digital signature algorithm. So we talk about, in classical cryptography courses, we talk about all those algorithms and their current standards, and probably all of you heard about all those algorithms and more or less how they work. However, we say that, well, if we will have a general purpose, large-scale, fault-tolerant quantum computers in future, then those algorithms will be affected. This is the definition that we kind of introduce in the course because we think it's really important that we have those three components. That is general purpose, which means, for example, you are able to run all the quantum algorithms, like Shor's algorithm on this computer, large scale, so we can actually do computations on a bigger scale, and fault tolerant, because quantum computers, they tend to have computations that actually have some errors there. So we will be presenting our experience in developing the course, what we included in the course, and I hope this introduction gives you a little bit of idea why we were motivated to do this work.
Okay. All right, thank you, Monica. I'm TJ, you might remember me from the introduction there. Just to go back a step here, yeah, so this general purpose, large scale, fault tolerant quantum computers, we wanted to add that to the description for the course because a lot of times people will hear of, this company D-Wave has a 2,000 qubit quantum computer, but that's not exactly comparing apples to apples with something like IBM, who would have several hundred or now up to 1,000 qubit computer. So another term that's often used here is cryptographically relevant quantum computer. So that's something that we want to keep in mind as well. Are we working towards that? Okay, so just before we continue on, any questions so far? I think we're going to try to leave it so that there's some time at the end, but feel free to ask questions. We are educators, so I know Monica likes questions. I love questions as well, so feel free to raise your hand at any point. Questions so far? No? Okay. Continuing on then. So NIST, who was mentioned in the keynote, right? National Institute of Standards and Technology, they basically put forth a paper, an internal report in 2016 that said we really need to look at this looming threat of quantum computing. What's going to happen if and when quantum computers get to the point that they are cryptographically relevant? Again, general purpose, can run any computer program, large scale, big enough to actually do hard problems, and fault tolerant, able to deal with errors in a reasonable way. So it turns out, somewhat surprisingly, and Monica already alluded to this a little bit previously, most of the problems seem to take place on the public key side, not on the private key side. So things like AES, maybe you want to go from a 128-bit AES to 192 or more likely 256-bit version. But that doesn't seem to be as much of a problem, at least given our current understanding of quantum computers and what they're capable of. However, things like RSA, Diffie-Hellman, Al-Gamal, and the other elliptic curve cryptography crypto systems that were mentioned previously, those are going to have an issue much more quickly and sooner than AES and things like that. So the analogy that I use in class is, it's kind of like you're trying to arrange the chairs on the deck of the Titanic. Don't worry about the chairs, worry about what's actually happening with the sinking ship. Anything else on this slide, Monica? I think this one's good, right?
I think we just might want to mention that, advanced encryption standard is with us to stay for a very long time. We will just have to increase the size of keys.
Right. All right. So the timeline for the development of this course was at RIT, when we were all members of RIT. Monica has, of course, since gone to U of R. We miss her terribly, but we must move on. So at RIT, we designed a new course to attract students that are interested in this future of cryptography and security and what's going to happen if and when general purpose, large scale, fault-tolerant quantum computers take over. So this is first offered as a master's level graduate course, but it's also open to very enthusiastic undergrads. So if a student had already taken the intro cryptography class and they wanted to take this master's level class, they would be typically allowed to do so. Of course, having passed the first class. That was in the spring of 2022, and the second offering was in spring of 2023. And then in 2024, so just last spring, we offered this in 2 schools because, as we already mentioned, Monica moved to U of R at that time. And it went, we decided to use a new name. It used to be post-quantum cryptography. We changed it to quantum-resistant cryptography. And again, both terms, we're essentially using them interchangeably. We feel as though that the quantum-resistant term is, quantum-resistant is a little bit more accurate because of the potential for confusion that the term post-quantum can have. If we have a little bit of time, I'll tell a slightly humorous story about that later. So now offered at 2 schools, RIT and U of R, both in Rochester, with plans to expand further moving forward. So a little bit about computational complexity. Who's a big computational complexity fan here? Anybody? Okay, yeah, we have a couple people. That's great. Good to see it. So basically, you've heard of classes of languages like P. That's the easiest one, typically polynomial time. You can essentially think of this as the class of languages, or the class of problems that can be solvable in a reasonable amount of time. Right, so most of the problems that we tend to encounter have a relatively low polynomial, so something like n squared would not be too bad, or even less than that, n log n. So that's problems that we can efficiently solve. You could think of it as that. And then many of you, especially the computational complexity fanatics here, would be familiar with the class of NP. All right, so now I'm going to put my professor hat on for a moment. Who knows what the class of NP refers to? Little audience participation here. Oh, Sasha, you can't answer. That's not fair. Okay, maybe if. So it's the class, anybody? All right, well, we'll move on. It's the class of problems that can be verified in polynomial time. So think of like a Sudoku puzzle, right? It might be really hard to solve the Sudoku puzzle, but you can very easily check if somebody else hands you a solved puzzle. You can say, oh yeah, you've got the rows of 3, the 3x3 grid. Yeah, that's really efficient, so to speak. The biggest open problem, arguably the biggest problem in mathematics and computer science today, is whether P is a proper subset of NP. That is to say, it's strictly smaller. Intuitively, it kind of feels like it is, right? That it's harder, there's some things that you can do that take more effort, but you can check them. And then there are other things that you can just do them more easily. Right? So intuitively it feels like these are different, but nobody has ever proved it. In fact, if anybody in this room or elsewhere is able to prove it, that's $1 million prize from the Clay Mathematics Institute, so you have a little bit of homework today. Anyway, if you do, by the way, 10% finder's fee. I'm not greedy, we'll just write the paper together and you can put our names on it. Anyway, let's move on. So there are some problems that are outside of P. So the aforementioned RSA, named after its 3 authors, Ravesh, Shamir, and Edelman, and elliptic curve cryptography. These are the hard problems, let's put that in quotes, hard problems that cryptography historically has been based on. Historically meaning since 1976, of course, that public key cryptography. There are other problems that we think may be a little bit harder, not necessarily as close, if you will, to NP, or sorry, not as close to P. But these problems, we want them to be hard because that's where the secret lies, right? If an attacker can very easily figure out the hard part of the problem, well, there goes the security of your system. So that's kind of the idea. These are based on so-called one-way functions or trapdoor one-way functions, where doing a computation in one direction is easy, but doing the reverse is very difficult, or again, thought to be difficult, and not thought to be in polynomial time. All right, then where do quantum computers fit into all this? Basically, it's not known precisely, but it's suspected that the class of BQP, and you can think of that as effectively the class of problems that can be efficiently solvable on a quantum computer. It stands for bounded error quantum polynomial time. It's kind of a mouthful, but BQP you could just think of as the class of languages that can be efficiently solvable on a quantum computer as an analog to P, the class of problems that can be efficiently solvable with a classical computer. Okay, everybody good so far? Looking for head nods? Good. Okay. So continuing on, BQP, we have kind of drawn this in with a dashed line here. This is from Nelson and Chang, the famous quantum computing, quantum information textbook. And so that, again, a little bit bigger than P, so there's some problems here that are outside of P that a quantum computer would be suspected of being able to solve, but for so-called post-quantum or quantum-resistant cryptography, we want to pick problems that are even outside of that bubble. So things that we'll talk about a little bit later, such as lattice-based problems, hash-based cryptography that's still very valid, and code-based cryptography, which Monica will be talking about in a little bit. All right, so any questions on this so far? Let's continue on. So due to progress, stop me when I don't want to trample over your slides here. I think I'm going up to a couple. Okay. So due to progress in the design of quantum computers, again, you always hear these announcements about so-and-so, IBM, Google, Microsoft, they've developed a however many 100-qubit or 1,000-qubit machine. So progress is being made. It's something that we definitely, as security professionals, I think all of us in this room, some form of security professional, would want to keep an eye on. And the ongoing effort from NIST, they don't want to call it a contest because they don't want to award prize money and announce one winner. There may be multiple winners. Anyway, following that, the development of PQC, there's clearly a need to understand what are the consequences of quantum computing. Where are we going with this? What happens when some of these problems that we thought historically were very hard for classical computers on a quantum computer would be very, much easier, much more reasonable? Where do we go from there? Threats of quantum computers to current cryptographic schemes, so the aforementioned RSA, Al-Gamal, Diffie-Hellman, elliptic curve, and then how to mitigate those by these post-quantum or quantum-resistant techniques. So after the third round, so if you haven't been keeping up with NIST and the PQC contest or selection standardization process, they've gone through several rounds now. At the end of the third round, they recommended, there was actually just one thing that they said, this one's okay to be standardized, called Crystal's Kyber. The official name now in the standardization is MLKEM, Module Lattice Key Encapsulation. Anyway, again, it's a mouthful, but the idea is it's based on, this is one of these lattice-based approaches. And then on the digital signature side, you have Crystal's dilithium, kind of the sister suite, if you will, of Crystal's Kyber. So the two of them are part of the same suite of applications. Falcon and Sphinx Plus. So of these four, those are the ones that they were approved to be standardized at the end of round 3, and now we actually have official standards for 3 out of the 4, Kyber, Dilithium, and Sphinx Plus. Falcon, we should be getting a draft standard sometime the end of this year or early 2025. So it's something to watch for NIST from updates. And then a few other algorithms that they said, okay, technically they're not eliminated, they'll advance to a 4th round. If we're not happy with the finalists that we have, it's nice to have kind of hedging your bets, so to speak. So if one of these doesn't work out for one reason or another, like you can see the column here for, on the KEM side, the public encryption side, basically replacing RSA for one, it looks a little bare. We only have one item there, one crypto system. So what happens if a critical vulnerability is found within that? You need to have a backup plan. So Bike and Classic Mikules were suggested, as is HQC. And then interestingly enough, and ironic given the name, Psych was also mentioned, but then a critical vulnerability was found in Psych just a month later. And so, yeah, it's no longer recommended for secure in a post-quantum world because it's not secure even in a classical world. This was broken with, there were some very humorously titled articles about this that said something like, you've seen them, right? That Psych was broken over the weekend with a 5-year-old laptop, something along those lines. So you can look those up. It's, it's funny, but it's not really funny. But you basically need to have a backup plan. All right, questions so far? Okay. So the selection process kind of whittled down. So in round one, that was back in 2017. So remember, NIST had that internal report in 2016, very informative paper, and then the contest kind of began in full stride the next year. Basically 69 candidates as of January 2018. Then a couple years later, or a year and a half later, down to 26 candidates in round two. By round three, we're down to 7 finalists and 8 alternates. For the reasons I mentioned, that you don't want to put all your eggs in one basket. If there's a critical vulnerability found, which has happened, and it happened as recently as Psych, you want to have something that you can kind of plug in its place. Standards available for these ones which I mentioned, so crystals Kyber, you can look this up, just FIPS 203, MLKEM. Crystals dilithium is the next one, sequentially, FIPS 204, MLDSA. And Sphinx Plus, FIPS 205, SLHDSA. That one doesn't quite roll off the tongue the same way. I like to call these ones MLKEM. I like to call it Malcolm for short. It's a little easier for me. MLDSA, Mildisa, sure. This one, no similar acronym, but I think Sphinx Plus is arguably the hardest to understand of these three. So it's somewhat surprising. We've talked about this within our group, that NIST would make these recommendations given that these are so new, but they have been developed over at least several years here since 2017. Draft standard, like we said, mentioned expected for Falcon sometime in late 2024 or 2025. I thought it was actually going to come out this summer, so they're a little late on that. And then 15 more signature proposals are also being considered. So this is kind of unusual for NIST to say, all right, we have this selection process, but we're not really happy with the candidates that we have, so there's an on-ramp for digital signatures. So if we go back to the last couple slides here, digital signatures, these are the ones that are recommended, and 2 of these 3, there's already a standard in place. Falcon is forthcoming, presumably, but NIST, again, kind of wants to hedge their bets and say, if people are concerned about security relative to performance, it's nice for them to have additional options on that. Anything to add to that? Okay, so moving on. Oh yeah, this one's Monica's, so I'll pass it over here.
Yeah, I think this will be more comfortable. I actually want to go back to the previous slide just to say shortly that if you're curious, all of those standards are on the NIST website. There is a software, you can download it, you can run it. This is what our students do for final presentations, okay? Also, I think what is really interesting here is that since you can run them, you can actually measure like how fast they are, and you can think like how it will work in future to put those pieces together. Okay, so let's look at our schedule, what we do over the whole semester. We decided that we want to do modules in our course which allows to learn certain pieces without necessarily going to other pieces of the course. That's not the goal for our students, but if someone else would like to just learn about some of those, then it's possible. Of course, we have to all go through introduction. So we do short review of current standards, RSA, Diffie-Hellman. What are the hard problems behind those algorithms, right? So we talk about discrete logarithm problem and the factorization problem. And then what's wrong with that and how it could eventually be solved with quantum computer. Before we get to quantum part, we actually look at the NP theory, and that's the really fancy slide that you could see that TJ presented with complexity classes. Okay, this is where it goes. So the idea is like, so hey, we have those problems that can be solved because there are some efficient algorithms, but we are looking at some other problems. So we want students to have a good understanding what are the other problems that we can use and why are they secure. The interesting thing is that actually we don't know if any of those problems will be secure in future, because someone might develop very efficient algorithm to break some of those problems in a matter of days, and it will be a kind of a disaster if you think about it. So we try to kind of phrase it nicely, make it interesting for our students so they don't drop the course, right? So that's our introduction. Then we move to the quantum part, because we think it's really nice to, we want to be secure against quantum computers, but like how they actually work, right? How are they different from classical computers and what can be done on quantum computers? We put quite some emphasis on the thing that results on quantum computers can produce some errors. but we are able to validate those if the result is incorrect in very fast time, polynomial time, right? With the Sudoku, right? I might not solve it so fast on traditional computer, right? But I can solve it faster on quantum computer, but I can verify it on traditional computer if it's actually the correct solution. Okay? And here we go over some quantum algorithms that we will tell you details about what quantum algorithms we go over. And after that, we have a few modules. So we can see we talk quite a lot about lattice-based cryptography. And you might think that these proportions there are kind of huge. But once we cover lattice-based cryptography, there are actually some of the problems there that are very similar to in code-based cryptography, which sometimes makes some of us think, like me, for example, what will happen if they break lattice-based cryptography? Does it mean that code-based cryptography is also broken? Because underlying problem seems to have kind of the same equation in a way. We also have a module on hash-based cryptography. And I think for many of us, this is actually our favorite candidate because Sphinx Plus goes here. And it looks like kind of it seems secure because it's pure combinatoric. We don't have any underlying path structure like we have with lattices or code-based cryptography. As you can see, we have one midterm exam in the middle of the academic year, so we don't overload our students. They have a couple of homeworks. At the end of the year, they have a final exam and students' presentations. We were actually amazed by many presentations that we had from our students because they did amazing work looking at the software, running it and trying to figure out what this code that is posted on the NIST website actually do, and they did really great in those presentations. So that gives a good idea and kind of we look happy into the future that we will have some people that understand the standards that are coming. Okay, so looking a little bit.
Can I say something about the presentations? Yeah, sure. Just a quick thing about the presentations too. The first year and even the second year, it was before the standards had been available in draft form. So they were a little bit more open-ended, and students could kind of pick. Okay, I think this algorithm has these advantages. This other algorithm or crypto system has other advantages. This last year, and we were all very impressed when we were teaching. This class at the students' presentations. They were allowed to work in groups, but they focused on the 4 that were about to be standardized or had already been standardized. So Crystal's Kyber, Crystal's Lithium, Falcon, and Sphinx Plus. The Falcon team had a little bit of a disadvantage because unlike the other 3, the draft standard wasn't available at the time, but they all did really well. And I think you said your Falcon group was it was a PhD student that did really well. So thank you.
Right. So in the first module, in the introduction, we basically, as mentioned, we talk about the consequences of what will happen if we have those quantum computers that are fault tolerant, right? Large scale, general purpose. That's important. So we can actually run all those algorithms efficiently. As mentioned in the previous slide, we do the review of the current cryptographic standards that are standardized by NIST and that might have to be replaced. Actually, they are kind of projecting that they want to move to new standards in 2030. What is really interesting is it's just 6 years. So if you would consider that companies would have to migrate and adapt to those new standards, right, that might be a bit challenging. They actually shortened that time because they were predicting that it will be 2040 just a year ago, and this year summer they said 2030. So they cut 10 years in 1 year when we are expecting to do that. But we already have 3 standards published, and we are waiting for Falcon. So. The progress in practical quantum computing, so IBM did some really great job there in 2023. They released their quantum machine. Then that had over 1,000 qubits. Then 2025, they're projecting to have about 4,000 qubits. That might seem like kind of a lot, but the thing is that you have to keep in mind that not all the qubits that are there are actually available for computations on those machines. Right? From some papers that we had a look at, was estimated at about 10%. So those are actually the available qubits that you can do something with those. Then Google claimed to have a quantum supremacy in 2019, which kind of was questioned, and it's, as you can see, we still use traditional protocols, right? And then 2023, Google did a lot of work on improving errors on quantum machines that they have. Also, IBM seems to have more qubits. However, it's also important that we want to have machines without errors, that to limit the errors that we have. So sometimes like having more qubits, it's not so much better if we have a lot of errors, right? So they kind of go in different directions in their research, right? Either more qubits or kind of like try to make it like with less errors. And we close the introduction with overview on those complexity classes with this very nice diagram that you could see, and where we were trying to kind of say like where the BQP class goes, the complexity class that reflects what can be done on quantum computers.
Thank you. So the next module was the quantum module. This one was really fun to do, looking at a lot of the quantum stuff. Students get pretty excited about it as well. This would be, even in class, it's a very high-level overview in a lot of ways, but we do, get into the weeds a little bit here. So general overview of quantum computing, kind of what was presented a little bit on the last slide, current progress being made, and expectations moving forward. For example, Google, these are the first 2 milestones in Google's 6-point plan to achieve general purpose, cryptographically relevant quantum computers. So they've, by some accounts, achieved these, although they may need to put an asterisk after the quantum supremacy one, as Monica alluded to. So we get into that, and then qubits themselves and quantum gates. So we do, simple gates, X, Y, Z, and I. And then very briefly discuss quantum algorithms like Shor's algorithm, which is an exponential improvement over the classical case. This is why, whereas Grover's is merely a quadratic improvement. So quadratic is great, you'll take it if it's offered, but the real game changer here being Shor's algorithm, and that would be more directly applicable to things like RSA, elliptic curve, and Algol. So Shor's algorithm is for period finding, and if we have a little bit of time, we'll show you a little bit of that here. And Grover's algorithm is more of a general approach. It's an unstructured database search. It basically cuts, if you're familiar with big O notation, it cuts the exponent in half. So instead of looking at something like 2 to the 1,000, you're looking at 2 to the 500. Okay, it's an improvement, but it's not necessarily going to be a game changer depending on other factors. So this is a nice slide. I stole this from Scott Aronson, who's written books and papers on quantum computing and computational complexity theory. This is from the book Quantum Computation Since Democritus. And so basically it's showing, this kind of hierarchy or this scale of going from easier problems up to harder and harder problems. So breaking RSA and factoring, they may be related. The only way we know of breaking RSA in reasonable situations would be factoring, but it could be the case that a classical approach to breaking RSA is found that doesn't rely on factoring. So those are so-called easy problems in the context of a quantum computer because of Shor's algorithm. You can apply Shor's algorithm to, again, let's say, cryptographically relevant, that's large scale, fault tolerant, all those things, general purpose computer, and efficient quantum algorithms are known. Going up the ladder a little bit to a slightly harder problem, so breaking all public key crypto systems that are currently available using trapdoor one-way functions. So if we think that this prospect, this idea of having a post-quantum world, a quantum-resistant world, then we would have to say, or we would hope at least, that this is something that's outside of what quantum computers can efficiently do. Otherwise, if quantum computers can just efficiently, subsume that as well, then the whole project kind of fails. Then, as you can see, private key, as we alluded to earlier, that is a little bit more resistant due to there's no known way to apply Shor's algorithm to the typical private key crypto systems. So you have to rely on essentially Grover's algorithm there, which again, quadratic is good, but not as good as exponential advantage. And then solving NP-complete problems on average. So I didn't mention NP-complete specifically on the slide a few slides ago, but you can think of that as basically the hardest problems in NP. So NP-complete, the hardest problems in NP. Can we solve those on average? Okay, that's getting harder. And then solve them even in the worst case. That's the hardest on this list. By the way, any questions so far? Yeah, sure. Yep.
What's the difference between a public key crypto system and a private key? Are they related?
Oh, yeah, right. So great question. Thank you. So this is something that the students would typically see in the first class in the sequence. So we typically gloss over that. But very briefly, the idea being with a private key crypto system, it's the same key that's used for both encryption and decryption. It's typically based on like a symmetric cipher, like AES would be an example of a so-called private key crypto system. Whereas the things that we're talking about with public key, those are the ones we keep mentioning: RSA, Algol, Diffie-Hellman, elliptic curve, those kinds of systems where you have a public component of the key and a private component of the key. So let's say Alice, we had Alice and Bob earlier. Alice publishes her public key. Anybody can send her a message, but only Alice, so that's public. So Bob sends her a message using the public form of the key, but only Alice would be able to decrypt that message. Is that clear? Does that make sense? Yeah, great question. Thank you. Other questions on that so far? By the way, I love questions. All right, hopefully we'll have some time for questions some more here. So I think kind of briefly here, I don't want to overwhelm people with some of the math, but we go into a little bit more of the detail of Shor's algorithm. So a naive problem or a naive algorithm for factoring would involve just trying all the possible divisors, right? Just simple trial division. You don't have to go too far. You only have to go up to the square root of n. But if n is very large, again, you'd still have to go, it may be computationally infeasible to do so. So some faster techniques exist. This is still in the classical realm. The quadratic field sieve and number field sieve, but they're still exponential in the number of digits in n. So again, Alice and Bob can pick an n that's large enough that doing it this way will still take too long for a typical adversary. So the idea with Shor's algorithm is to factor n into p and q. So p and q would be large primes that are chosen. Those are kind of the secret information here. And by doing that, or the attempt to do that would be finding the period with respect to r in the sequence x to the r mod n. So it uses modular arithmetic, and it turns out that based on some number theory, you can estimate or you can guess what you think the answer is going to be based on this so-called period, based on how often this value is going to repeat. So that's kind of in a nutshell what takes place. This may take a very long time classically if n is large, but where do quantum computers come in? One crucial step is if we have quantum computers, we could take advantage of these superpositions of states. You may have heard of this. So if you have things that are kind of like waveforms and they're acting in superposition where things that are positive can kind of add up to one another, things that are negative also go in a downward direction. If you have one positive and one negative, they kind of cancel out, and everything in between. So the analogy that I'll often use in classes, it's kind of like if you picture a perfectly pristine pond and you throw a rock in it, you get these ripple effects, right? These waves. And then if you throw another smaller stone, you'll get ripples that kind of bump into each other, and some of them will kind of be added up, and others will cancel each other out. And so you could take advantage of that effect in a quantum computer to efficiently find this period. So how does that look? You can ignore this math here. This is just the discrete Fourier transform and its quantum analog. Don't have to worry about that too much. Basically, the idea is we have three phases to the Shor's algorithm. First, turn that factoring problem into period finding. Now, that can actually be done classically. You don't need a quantum computer to do that step, and more likely, you don't want to waste the resources, so to speak, of a quantum computer to do that, since it can already be done classically. This is the quantum step. Find the period using the quantum Fourier transform. This is the step that would be very inefficient to try to do classically, but it's where you get the advantage in a quantum computer. And then the last step, use that period value to find the likely factors. Notice that word there is doing a lot of work, likely. So that means that, this can fail, right? You may have to run it more than once, but it's not a big deal because it's so efficient that even if you have to run it a few times, the net effect is it's going to be faster than the classical case. Again, asymptotically that would be true for large values of n. All right, questions on that? I think that was my last slide on quantum.
Okay, so the next module is lattice-based cryptography, and the idea is that we start with preliminary on matrices, and this kind of nice picture summarizes how the encryption actually work. So if you would look at S vector, okay, that's the secret. You have two base vectors, B1, B2, and in two-dimensional space, this problem actually looks really easy. And then the lattice is basically the set of dots that you can see there. So you take those base vectors and you look at all the linear combinations that you can get out of those, considering that the coefficients are integers, okay? Which basically ends up to be those little dots there that you can see some of them. That's the lattice. The idea here is that if I have a secret, which is some kind of vector, not necessary in the lattice, so whatever is in the lattice ends up in a dot, okay? Now, if Alice, okay, used certain secret, and by using this secret she generated publicly known matrix A, she is able to encrypt. I mean, she will share the A and everyone are able to encrypt and send her message, okay? Now, that would be kind of easy, maybe to reverse, so error is added. Now, if you have the secret, you kind of have huge advantage of removing this error. If you don't know the secret, removing this error is really hard, and actually the error looks bigger if you don't know the secret. So the idea is that when you encrypt, you see A, Alice published it, so you multiply A by S and you add some error, okay? So from the green vector, after adding error, you end up having T, which is the encrypted message, and you see that the purple vector T doesn't end up in a dot. It's not in the lattice, okay? And that's the encrypted message. That's this vector. Now, the idea is if you know the secret, you are able to reverse those computations and get rid of the error, but if you don't know the secret, the A is constructed in a way that you are not able to efficiently remove those errors. Okay? This relates to shortest vector problem, which relates to closest vector problem. So how can you find the closest vector to T, but one that is actually in a lattice? So that's the underlying problem that this refers to. And those boxes on the bottom of the slide present matrix A, secret S, you add error, and you get encrypted message that only Alice is able to reverse those computations to get the original S, because she has additional secret knowledge about how the matrix A was constructed. There are some algorithms that are effective for low-dimensional lattices, so LLL algorithm. We also review with our students algorithms on lattices that were broken. Still, we are going to use it in future. So it's interesting to see that, how it was done, and then to understand what kind of improvement needed to be done in the future. So we do Goldrake, Goldwasser, Halevi, and Hermit normal form public key crypto systems that were broken, and we show attacks on those. In the hash-based cryptography, which is Sphinx Plus, and we are big fans of this one, we review hash-based cryptography, then we talk about one-time the signature that can be used only once. So you publish hash, and you keep as secret the pre-image, and then to prove that it was you, you share the pre-image. If they can compute the hash and compare with the published one, they know it's you. Okay? But the problem is that it works only once, right? And you know that you have to authenticate also public keys. That's the problem. So then we go over the Winter needs one-time scheme, which allows you to actually sign more messages. And then we don't go over details of the Sphinx Plus that's left for students for presentations. However, that's we kind of like put some of the pieces and ideas there so that students can do the rest of the work. In code-based cryptography, those codes, you send messages over communication channel. If there are errors, you are efficiently able to remove those errors. Surprisingly, this is done for encoding information, but the same idea can be used in cryptography to encrypt information. So we talk about basics of those codes. We go over with details about GOPA codes because they're the best codes for this type of cryptography. How to efficiently decode, okay? We have to know the structure of the code, actually. But if you keep the structure of the code secret, then you are not able to efficiently decode. Okay. The next idea is that what is the idea behind code-based cryptography is the same like lattices. You have a vector S, you multiply about some matrix, generator matrix of the code, you add error, you get another vector. But to decrypt, you use decoding algorithms. If you have knowledge about the structure of the code, you can reverse it. Okay? And then we talk about some attacks on those, just to make things more interesting and make our students think a little bit more how it can be attacked.
Thank you. All right, in the interest of time, it's okay. I'll just go through this a little bit quickly. So in terms of the class, like we mentioned, there's been 3 times where it's been offered, 3 semesters, and now at 2 schools. We think what worked really well, the topic selection is pretty well received, and the modular design, that's something that we kind of switched to. We were, more or less the first time, we were trying to put things together in a more hodgepodge manner, but the subsequent times we were able to spend a little bit more focus on kind of a modular design. Use of a really great tool, Sage or Sage Math, that has a lot of cryptographic primitives already built in, and then students can use that to build on it. Homework design and the presentations, we've already mentioned, that were really great. I think everybody, all the students learn. We, as instructors, always learn from those as well. Some challenges, dealing with students' different and varying mathematical background. As you might imagine, a course in quantum cryptography, not quantum cryptography, but post-quantum, quantum-resistant cryptography, there's a little bit of math involved. So we try to let the students make it clear with the expectation there. They don't have to have something like linear algebra 2, but linear algebra 1 and the intro cryptography class is prerequisite. More examples for classroom use. We've been slowly adding things in as we go. And focus on the evolving NIST process. So because it's an update, right? Every year at least, NIST has a few updates to the selection process. So we want to be aware of what they're doing and kind of guide our instruction based on that. And then links between some of the advanced math and algorithms. We want to provide, as Monica kind of alluded to, we don't cover Sphinx Plus formally. We leave that to students to explore, but we want to give them enough scaffolding so that they can do that.
And this is just some statistic. We just wanted to say that as hard it might seem at some moments, actually we had a lot of students that successfully completed the course. That's our enrollment. So we started with 14 students, very brave students because we were running it for the first time, but they kind of like, oh yeah, I go for that. Why not? Then next year we had 22 students, and then we had 17 students. At U of R, which doesn't have like big cybersecurity center at RIT, but we started with the course there with 10 students enrolled, and this is when we actually started to deliver it to PhD students also. We have a good percentage of female students actually, as you can see in all those courses, which is really great in terms of diversity. And then we have some grad students, and what that means, grad student, means also we have undergraduate students that successfully ended up completing this course with great grades. So we definitely think that this course is accessible. And we also have really good reviews from our students, so we can say that they overall rated us as excellent or good in most of the categories. They said that it was overall really excellent, some said good, course objectives were really good, course content was also rated high, how we organized it, and also assessment methods. So they enjoyed homeworks and exams, right? So I think that's really great for us as instructors.
All right, and then really quickly, we'll open it up to questions. So like we said, 3 instructors now at 2 institutions, other things in the works. Material is always evolving. Let us know. We wanted to do this partly as an outreach to industry, to get ideas from industry folks and kind of open up a dialogue. So please get in touch with us, and we would love to hear from you. That's our talk. We'll open the floor up for questions.
Do your students work in labs, or do they have to have really heavy-duty laptops?
Yeah, no, that's a great question. So, we work in actually a traditional lecture room. So it just has, desks and a whiteboard up front, and then programming assignments that they do. They can, fortunately, they can do it on a traditional computer. They don't need a quantum computer. They don't even really need like a resource-intensive computer because they're exploring one aspect of this. So they're exploring it in a mathematical way, and it could sometimes reduce a reduced version of the problem to kind of make it a little bit simplified. For the student presentations, we encourage the students to run a very small example of something like Sphinx Plus or crystal xylithium that they can do on their own computer, their own laptop. And it doesn't have to be anything fancier than just a regular couple-year-old laptop.
So I want to add that those NIST standards that are published, there is code available. And it runs really fast on traditional computers, so no special computer is needed. Everyone can run it on regular laptop.
Great question. Thank you. Other questions? Yes?
Just on your personal perspective from your book, based on cybersecurity, the way things are in the industry, what do you feel is the biggest challenge from the cryptography side?
Biggest challenge. Do you want to start first?
I think the challenge is that some things are new. We think that students who took traditional cryptography courses don't know those standards. Most students didn't even hear about what is lattice before coming to our class, or some students didn't even know what are error correction codes, because this is not in the typical CS curriculum. So the challenge is the math structures. At the end, you kind of just want to understand the product, right? And kind of like know what it does and put the pieces together. But it's kind of nice that you have some idea what's happening inside there. Also from the perspective that, there might be potential attacks on those crypto systems. Really good thing for us that I forgot to mention before. Those are not new crypto systems. They were with us since 70s, 80s. NIST actually is very happy with that those are not new algorithms, because if something is with us for a very long time and no one broke it, this is what we would like to adopt. Okay.
Yeah, I would just like to echo that, the fact that some of the systems like Mikulic's 1978, so it's been around for a while, but now, getting industry to adopt it and more people to adopt it in general, that's kind of been the challenge, right? So you want to consider these things over a longer time frame. It's not just snap your fingers and everything is immediately in a post-quantum world. And even, some of the big players like Google and Microsoft and Apple have already started to roll out these so-called hybrid systems that they'll say, okay, we're going to start on-ramping some of this post-quantum stuff in addition to what we're already doing. So that's kind of what we view as a challenge here. Great question. Thank you. Other questions? I think we still have a couple minutes, right? A few minutes for questions. We love questions. Yes? Oh, yeah, okay, so I'll tell this story, thank you. So we were thinking of the idea for the course, and so we had a previous chair that had recommended a few things and said, maybe you can look into this, and this chair actually brought the three of us together because we were all looking at different aspects of it. I have a degree in physics, an undergrad degree in physics, obviously we're all computer scientists, and so we were really kind of racking our brains. We were like, oh no, what should we call this class? And there seems to be a lot of confusion between so-called post-quantum and quantum computing. This is not a quantum computing course. We do touch on some of the aspects that are involved in quantum computers, but that's 2 weeks. The rest of the course is what can we do classically to prevent a quantum computer from attack? And so we were really worried about this, and but then our boss said, oh, it doesn't matter. As long as it has quantum in the title, that's all we're interested in right now. Okay.
I might want to add that we had a certain problem with the approval committee for the course.
Right.
Because they were kind of like, so what is post-quantum? So we want to teach cryptography without teaching quantum computations first in the entire course.
Yeah.
I think so that was kind of like, the name is misleading, post-quantum, what will happen after we have quantum? So people have a tendency to think it's not quantum computers, when it's actually no, and there was discussion like, why we name it like this? Well, NIST names it like this, so we just follow.
That's right, yeah, we were trying to follow the NIST convention, but it led to some confusion even within the department, so I thought it was funny, but yes?
Is your class offered online?
Not currently, but...
Not at this time, but who knows, maybe we will change it in future.
Yep. Yes?
Implementing some of these things in industry? I'm thinking how RSA is 50 years old and we just keep increasing the key length.
Right.
Cryptography is hard, certificates are hard, so people just don't want to learn it and change. So.
Yeah, Monica, do you want to take that one?
What I really like, if you would actually look at the documentation for standards, I think NIST did amazing job. Just looking at our students struggling with presentations before those standards were published. And those standards so well done, all the notations there are so clear that I think it helps a lot. So just the documentation that is done. But realistically, we don't believe, like most of us, don't believe that we will have actually quantum computers that are threat in 2030. I just think they want to be really secure. Kind of like, let's be prepared ahead of time so we are really safe in future, no matter what it happens, just in case.
And just to add to that, so there's this thing called Mosca's inequality, which is basically the time that it takes to develop these systems and roll them out. You want that to be shorter than the amount of time that it takes to develop cryptographically relevant quantum computers. So it's MOSCA, I believe. If you look at that, that's the thing that you want to start to think about, and kind of going back to your question of industry rollout. Yeah, okay, maybe it's not going to be immediately just flip a switch and we move over, but there's also, you have to be aware of, this kind of capture now and decrypt later threat, right? So, okay, even if quantum computers are not available now, if there's some traffic that we want to protect for the next 10 or 20 years, it's something that we want to be aware of.
Or if your company cooperates with government.
Sure, yeah, within government, had to follow the NIST recommendation. Okay, we good for time? We have time for one more question or two more? One more, okay, time for one more question. Anybody, if you have? Okay, sure, we have Mike.
I'll ask.
Sure.
What number of qubits do you think need to happen before we need to start worrying?
Right. Monica kind of talked about this a little bit. You want to take that one? Or do you want me to?
I think it's a bit hard because that relates to this, that not all the qubits are actually what you can use. So you have to kind of account for those 10%. And from 4,000, we end up having 400. And if you think about key lengths that we currently have, so 256 bits, right? That kind of relates, but that's advanced encryption standard that will stay for us. So it's not just the space where you store it, right? But you also have to think that I have to also have the algorithm running and space for that and the system that is on this quantum machine. But I think it's really hard to answer. Also, you have to account for the errors in quantum computations, how often they happen, how much they affect results. So I would really say it's a hard question, and probably many people would like to have answer, but
I'll stick my neck out and say 1 million and then 1,000 logical qubits that you can actually do something with. So once you get to that benchmark, I think that's where you can start to make some progress on this and talk about cryptographically relevant quantum computing. But that's not necessarily industry standard. But all right, well, I think that's all the time we have. Thanks, everyone.